Today we are talking about phase changes, which is chapter 3.3. So a phase change is a reversible physical change that occurs when a substance changes from one state of matter to another. It's a physical change because the substance itself does not change. It just goes from one state to another, say plasma to solid. Melting, freezing, vaporization, condensation, sublimation, and deposition are 6 common phase changes, and we'll talk about all of them. Melting, as you all know, is when a solid goes to a liquid. Like you can see in this picture here, the rock has become so hot inside this volcano that it has turned into a liquid. It melted from solid rock to liquid rock. Freezing is exactly the opposite. It's when a liquid turns into a solid. So once this lava cools, it will lose some energy and it will turn back into its solid state. Vaporization is when a liquid turns into a gas. This could be by boiling, adding heat, and getting a substance up to its boiling point, or it can be done by evaporation, which is where the particles on the surface of the liquid leave the liquid and become a gas before the boiling point is reached. Condensation is exactly the opposite. Anytime you have a gas that cools and condenses into a liquid, that's condensation. I just used the word right there, condenses. This is a picture of liquid nitrogen, and we tend to think of vaporization as happening at a high temperature because we usually base things on water. We say, oh, freezing happens at really cold temperatures and vaporization happens at hot temperatures. That's not necessarily true. It really depends on the boiling point or the freezing point of the material. So the boiling point of liquid nitrogen is somewhere between 60 and 70 degrees Kelvin, which is about negative 200 degrees Celsius, which is really, really, really cold. But it's still boiling at that point because that is the temperature at which those nitrogen molecules want to become a gas. And finally, sublimation is when a solid skips the liquid state to turn into a gas. And deposition is exactly the opposite. It's when a gas skips the liquid phase to turn into a solid. Dry ice is a great example of sublimation. And an example of deposition is when frost forms on a window. The frost comes from water molecules that are in the air, and as those water molecules cool down, they form little frost droplets on the windows. Now, one way to recognize a phase change is happening is by measuring the temperature. And this is because the temperature of a substance does not change during a phase change. Let me say that again. The temperature of a substance does not change during a phase change. That sounds really weird because you would think, okay, I usually need to heat up a liquid to get it to vaporize, or I need to cool down a liquid to get it to freeze, which is true. But once that process starts to happen, the temperature will no longer change. As an example, I have a picture here. I have time on my x-axis and I have temperature on my y-axis. And what I'm doing here is I'm taking solid water, ice, and I'm heating it up over time until I can get to gaseous water. As I do that, I have to put heat into this. And I'm putting in heat energy the entire time. But as you can see, down here, from here to here, I'm putting in heat that entire time, but the temperature is not increasing. It's staying pretty flat. That's because all of the heat energy I am putting into this thing is going into melting those particles and breaking the bonds between them so that they can freely flow in the liquid state. Once it's in the liquid state, you can see it hits this plateau again, right here. This is where the temperature is not increasing anymore. This is boiling. This is where all of the heat that I'm pumping into this system is going to breaking the bonds that are keeping those particles close together in the liquid so that they can fly apart and become a gas. Now, a much clearer picture of this can be seen if I show you a different diagram. This diagram is one you would be likely to see if you were to take data on temperature over time in a phase change lab on yourself. But This is one that is more widely accepted. You can see it's a bit blockier, which isn't really realistic, but it shows a really great phase change curve. That's what we call it. So here, let's say it's a solid, and that solid's getting warmer and warmer and warmer until it reaches the melting point. At this point, from there to here, all of the heat that's being put into this is going into melting that substance. None of it is being used to heat that substance up anymore. Once all of the particles are now in the liquid phase, the temperature will start to rise along with the temperature again. So, I know it's a weird thing to think about, but it's super important. The temperature of a substance does not change during a phase change. Now, phase changes are all about energy. Energy is either absorbed, taken in from the system, or from the environment around the system, or released, let go into the surroundings during a phase change. There are two different kinds of changes, and the first one is called an endothermic change. Endothermic change means the system absorbs energy from the surroundings. And examples of this are melting, vaporizing, and sublimating. In all of these changes of phase, energy needs to be absorbed in order to go from one state of matter to another. That's endothermic. The other kind is exothermic. And during an exothermic change, the system releases energy into the surroundings. It needs to get rid of some of that energy in order to make that phase change. And examples of exothermic changes are freezing, condensation, or deposition. Now, the energy changes during a phase change relate to how the particles behave. So we talked about the kinetic theory of matter and how all matter is made of particles, and the way that those particles move around and interact with each other will dictate what phase it's in. Well, this has a really, really important role in phase changes. The arrangement of molecules in a substance become less orderly as a substance melts or vaporizes, and more orderly as the substance freezes or condenses. And you can see that in this picture here. We know that in a solid, the particles are vibrating, they don't have a lot of kinetic energy, they're pretty closely packed together. As you melt that substance, the particles start to move more and more. They have a less orderly arrangement. They're kind of moving all over the place in random directions. And if you vaporize that into a gas, the particles are even less orderly. They're all over the place. And if we were to condense the gas into a liquid and then freeze the liquid into a solid, you would see more and more order and less kinetic energy coming into play here. Now, it turns out that I can't just put the same amount of energy into water to get it to boil as I can to put into liquid nitrogen to get it to boil. Just like every substance has its own boiling point, the temperature at which it will boil, every substance has its own what's called heat of fusion and heat of vaporization. And these are specific numbers that tell us how much energy needs to go into that substance to get it to change from one phase to another. So, when water melts, it requires a certain amount of energy per gram from the surroundings. It needs to take in 334 joules, which is our unit for energy, and we will add this to our concept chart. It needs to take in 334 joules of energy to melt 1 gram of water, and this is called water's heat of fusion. So when you think of fusion, you can think of things fusing together, and that's exactly what happens when a liquid becomes a solid. The particles kind of fuse together and those bonds become really strong. So in order for water to go from a solid to a liquid, it needs to take in 334 joules of energy per gram. The opposite is true if we want to go from a liquid to a solid. If I want to go from liquid water to solid water, I would need to get rid of 334 joules of energy per gram. This also happens with boiling. So similarly, when water vaporizes, it requires a certain amount of energy per gram from the surroundings. It needs 2,261 joules of energy to vaporize 1 gram of water, And this is called water's heat of vaporization. So what that means is, if I want liquid water to become gaseous water, I need to add 2,261 joules of energy from the surroundings. That's crazy. That is way more energy than I needed to add to get it to go from a solid to a liquid. And that's why boiling is such an energy-intense process. For every gram of water, you need way more energy to get it to boil and become a gas than you did to get it to melt. And you can see that here in our phase change curve. When water is a solid, we put energy in and it heats up. And once it hits this first plateau, this is the heat of fusion. I have to put in 334 joules of energy per gram in order to get it to go from a solid to a liquid. And all of the energy I'm putting in this, all of the heat energy, goes toward that heat of fusion, goes toward the process of breaking the bonds between the particles and changing from a solid to a liquid. Once that's happened and I've reached my 334 joules per gram, it will start to heat up again, and that liquid will get hotter and hotter and hotter until we reach the boiling point. And here is the heat of vaporization. So at this boiling point, I need to keep putting in heat until I get 2,261 joules per gram, and at that point, all of the liquid will become a gas. Now, just to show you a little bit of a picture of what this will look like, if it wants to work, which it doesn't. So I'll show you this in class. But basically, when you think of phase changes, think of the particles, and you need to put energy in to move those particles around so that they become less orderly. As that happens, the phases will go from solid to liquid to gas. If we take energy out, those particles will become more orderly, and that's when we go from gas to liquid to solid.